Hello and welcome back to Physics for the 21st Century. My name is Greg Perugini and this topic is Archimedes Principle. And this is a principle of buoyancy. Because when you think about it, if I have, let's say, a tank of water here, and I have a cork. If I'm going to put that cork in the water, it's going to float. If I want to have it totally submerged, I'm going to have to put a force against it. I have to apply a force. Now, it also has a force of its own, right? Based on gravity. The force gravitationally is its mass times the g constant, the constant for acceleration on this planet, 9.8 meters per second. But that's not going to be enough for a cork because its density, if you remember, we have density, mass over volume. Its density isn't strong enough, isn't better than the density of the water. Now, what Archimedes came up with is that it has to deal with the amount of the fluid that is displaced. If I go into a bathtub, the water is going to rise, be displaced by my volume. But the buoyant force is going to be the density, not of me, but the water, times gravity, times the volume of the water displaced. Not me. So it has to deal with the density of the water and the volume of the water displaced. Now, it's true that if I am totally submerged, the volume of the water is equal to the volume of me. So you have this upward force of buoyancy, and it's a factor of density and volume, and the density of the object doesn't factor in, but it can be used to calculate the volume of the fluid displaced. Let me show you an example here. And as I said, this was Archimedes, and Archimedes was first given the problem of a crown. The king gave him a crown and said, "Is this gold or not?" He says he asked him to weigh his crown and to figure out whether this was gold or not. So he put it on a scale, and I'm going to write down Bernoulli's equation again here. Okay, density of the fluid times gravity times the volume of the fluid displaced. So he gave him a crown and he measured it in air. In terms of its weight, it was 7.84 newtons in air. But then he measured it in water, and he found that it was 6.84 newtons in water. Well, why do we think that is? If you think about it, there must be some sort of force that is causing it to weigh less. The difference between these, 1 newton, is the buoyant force. Up 1 newton. So how can we use this to calculate whether it is indeed gold or not, the crown? Well, if we look at the density of the fluid displaced, we already know that the buoyant force is 1. The density of the fluid displaced is water, which is 1,000 kilograms per meter cubed. Times gravity, times the volume, now we could solve this equation for the volume, right? If you look at this equation and you solve for the volume of the fluid displaced, that is going to be equal to what? 0.000102 meters cubed. A meter cubed is a fairly large piece of volume, so you would expect the crown is not going to displace too much. And given that it is totally submerged underwater, that also equals the volume of the crown, the volume of the fluid. We also know that density of the crown is equal to mass over volume, mass of the crown. Well, how do we get mass of the crown? Well, if we know that it weighs 7.84 newtons in air, we know that we could figure out the mass, right, by taking 7.84 and dividing it by 9.8 to get the mass. 0.8 kilograms. So, the density of the crown then is equal to 0.8 divided by the volume of the crown, 0.000102 meters cubed. So we could get the density of the crown. Turns out, give you a second to do that math. So that is 7843 kilograms per meter cubed. Now, we can look up in a table what the density of gold is. If we look that up, it's about 19,300 kilograms per meter cubed. So that automatically tells us there, when we compare these two, that the crown was not gold, right? This number does not equal this number. It's some sort of alloy, or maybe it's hollow. We know the density of gold, and we now know, based on the weighing of the crown outside of the, I'll put this back here, by weighing the crown in air and then weighing it in water, coming up with the buoyant force, and then using Bernoulli's equation, we were able to find out the density of the crown and hence compare it to the density of gold. So there you have it. That's Bernoulli's equation there. And again, you see the factors there. The density of the fluid displaced is a factor in the buoyancy. Most people, this is one mistake that you get often. They figure that if you're given the density of the item, whether it's a cork or whatever, that you're going to use that here, and that is not the case. It's the density of the fluid displaced. Now, the volume of the fluid displaced can be equal to the volume of the crown if it's totally submerged. The object, whatever it is, it could be a crown, could be anything, right? But the density of the fluid displaced is what matters. Okay, so that's what matters to the buoyancy. In this case, we were using water, right? The density obviously changes, and the buoyant force would change if we're using some sort of other fluid. So know your way around that equation. Remember how to calculate density, and you may be given the density of the particular item, and that will give you a mass and a volume. And the volume, if it's totally submerged, could be the volume you use in your Bernoulli's equation. So whatever is being submerged, remember, we're talking about the density of the fluid and the volume of the fluid. And gravity is also working with you in a sense, right? If I am, let me show an example here. If I have a cork, like I said before, and it's totally submerged, I have created a tension on this rope because the buoyant force is greater than the force of gravity down, just smaller amount. A cork doesn't weigh much. And hence, in order to have an equilibrium here where it's not moving, you have a tension on the rope added to that. So be aware, that's a typical type of problem. Either I'm trying to figure out what kind of force I must place to hold it under, or it's being held under by a rope. So there's a tension. Let's say this was an iron ball. Obviously I have a tension here because the force of gravity for an iron ball, right, is greater than the buoyant force in this case. Hence, I have to have a rope of some sort, and there would be a tension here. So think through these type of examples, and you should be ready for the assessment. Good luck.